I have a little bit of a different presentation today. Its scope is too big. The slides have way too much text on them, and it can be to a very narrow audience. It can also be to a very broad audience. So just to get things started, I would love to learn how many people have heard of a bootloader before. Could you raise your hand? That's great. How many people work more with MCUs and RTOSes as opposed to Linux or operating systems? So MCU, okay. So in the MCU world, you probably have a little bit less bootloaders. There are boot ROM, you might be familiar with that, so this might be less applicable to you. I'll try and make it broadly interesting to everybody. Before I get started, I want to make a quick shout out to a really cool organization here in Munich. In the Alte Gasteig, there is a Werkzeugbibliothek. So it's literally a place you can rent tools. You can get a cotton candy machine. You can get pizza ovens. You can get everything you would ever want. It's a nonprofit organization, and they're developing their own rental boxes like you get with DHL or Amazon. They're doing a new design themselves. So if you are a mechanical engineer, you're an electrical engineer, you like software, I definitely recommend reaching out to them. It's a really good, interesting thing. Even if you just you need a tool, you need to drill something in your wall, it's a great place to go. So a little bit on my background. I have worked on many different things, we'll talk a lot about Linux, but not just Linux, some RTOSes. There was a really cool processor out of Ireland, the Myriad X from Movidius that was bought by Intel. I'm a big fan of Buildroot in particular. Used it for many years. If you're a Buildroot user, this feature in particular was very exciting at the time. And I've worked with everything from these sub 1 watt vision processing units to Xilinx SoCs with built-in fabric and FPGAs. I've also been active on the OSFC Slack. So there's actually an open source bootloader community. Probably nobody here has even heard of it. I can do a quick poll if anyone has heard of OSFC, probably not. But this is really the community-based approach to bootloaders. It's a very small community. And this year, I've joined the TSC of Linux Boot, which I'll explain a little bit later. I've also worked at a number of these kind of boutique Linux consulting companies here in Europe. Only 2 of them so far. I'm still missing a lot of other ones. There's a whole myriad of different ones. So I have kind of a broad background. In particular, though, I've approached this talk about bootloaders from a broad perspective at first. So maybe you think bootloaders and you have some vision in your mind of what that is. But fundamentally, it's the same type of software that's going to run as an operating system, a real-time operating system, or bootloaders. These are all just programs that run on computers. And the really important thing to remember throughout the talk is that whatever your experience is right now with writing software and hardware, it's very different than everybody else. So if you work on RTOSes, if you work on SDKs, if you work on Linux, it's a very different experience, and that's based on the history of these projects, the history of this software. We're going to stick mostly with Linux kernel because the community-based approach to development is really the best and most powerful way to develop software, really in history. From the hardware side, we're not just leaving that behind. Although hardware tends to be more closed, there are important key changes here. One of those is that chips are getting bigger and bigger, right? We get new packaging technologies, we get Moore's law. That means that embedded is no longer the same embedded it was 10 years ago, even if you're on a microcontroller. At the same time, embedded is very different than the PC market or the server market or a lot of these other types of computers. And in one key way that's not always appreciated, and that's competition. In x86, you have AMD and you have Intel, and you get almost no information about how those chips work. In embedded, you get hardware reference manuals from vendors that have detailed descriptions of how chips work. That's something not to be underestimated. that has a huge impact on software and how it's developed. So, yeah, what is a bootloader? Apparently everybody's an expert, right? From a brief overview, we start with a boot ROM. So people have heard of bootloaders. How many people have heard of a boot ROM? Okay, that's awesome. So maybe half-ish, a little bit more. Boot ROMs are the thing of proprietary internal vendor-specific code. This is the first code that executes on a chip when you power it on. And in general, on the x86 side, you will never have any understanding of how this works. Nobody does, except if you work at Intel or if you work at AMD. If you work in the embedded space, you might have a little bit of experience with this, but probably it's still highly secretive. So then this boot ROM basically does some basic initialization. It reads some data from somewhere. It could be Ethernet. There's boot ROMs. TI, for instance, has a pretty advanced ROM in some of their chips that even allows you to directly load from Ethernet into SRAM. But basically, you make a very resource-constrained application that's fused into the chip. It can never, ever be changed. And so, as that sounds kind of scary, you can write your code. It gets written onto the chip once, and you never, ever get to update it again. So obviously you want to keep that kind of small. After that comes a whole set of initialization. The most critical for most systems is DDR initialization, because it's a particularly complex step and also takes a lot of time. But more generally, it's a question of finding the next stages that can do special hardware initialization, load the next stage, eventually allow you to get to a runtime operating system. So we have boot ROM, we have some hardware initialization, and then eventually we get to your application or your operating system. Ideally, if I had a bit more time, I would also show you some of these boot flows. You can check these links afterwards. There'll be a number of them in the slides. But as you can imagine, boot flows can get incredibly complex. You can have multiple cores, you can have proprietary firmware, you have shadow cores, you have ARM trust zone. Modern SoCs are wildly complex. They are incredibly complex computers in their own right. As such, how things load and run on these chips, it results in these wild diagrams from different vendors. So we have a boot chain. You have a ROM, you have some different stages that does hardware initialization, eventually you get to, let's say, Linux. That sounds great, right? But there are a lot of practical problems. So when you think of your own software ecosystem, you think of if you're in RTOS land, or you're in microcontroller SDK land, or you're in Linux user space or Linux operating systems, all of these ecosystems have their own qualities. Bootloaders are particularly challenging because there's limited vendor documentation and there just isn't a big community. Like I said at the beginning, no one's heard of OSFC because there's probably a few dozen people that are working in this open source community world. Most of this comes from vendors, most of it is poorly documented, and as such, it's a very, very small community. That means it's fractured. There's many different implementations across different projects, and in fact, it's so bad that operating systems in themselves include bootloader initialization because there's failures in the bootloader. So on the x86 side, the kernel has had to take on compression inside of the kernel, add an extra stage. There's a separate application that gets compiled into the Linux kernel that runs before the kernel runs, if you want to support a kernel with compression. And that's primarily because these boot chains, the loaders of the operating system, are not accessible. We can't change them, we can't hack them, we can't modify them. That's also true of user space. Systemd, very prominent in Linux, it's now pretty much everywhere, also is developing its own bootloader, which is kind of crazy. Your quote-unquote init system and Linux user space has C code that is actually implemented as a bootloader. So it's not just user space anymore. Yeah, so there are some open source bootloaders, there are some open source communities out there, but they're fragmented, they're small. On the x86 side, you may have heard of UEFI. or previously BIOS. This is, again, I keep harping back to this idea of how software developed. But if you look at RTOSes, you look at Linux, you look at any piece of software you can think of, when was a standards committee the right approach for writing software? And that's where you get into the x86 world. Is it really the best approach to create hundreds of pages long documentation to tell you how you should write your software? So x86 has definitely not solved these problems any more than it embedded. And then fundamentally, there's no boot chain. So that thing I just described, it's not like you can go to a website and download a boot chain for your own board or a number of different boards. So there's an ecosystem that exists, there is some community, but it's not that well organized. So what are how can we make some steps forward? And where are there some highlights? So here I'm focusing, I work for Analog Devices, a little bit biased. But there are some good examples from a set of chips that I'm working on at Analog Devices that can be taken to other vendors that other vendors undoubtedly also do. ADI, in the public HRM, the hardware reference manual that any of you can download that you don't need to create an account for, there is an extensive documentation of the boot ROM. That is astonishing. If you don't spend all day thinking about bootloaders, maybe not so astonishing, but this is a very, very, very rare occurrence. ADI is also trying to do a lot of other things where for these DSP processors, mainlining into Linux, U-boot, Buildroot, we've set up a GitHub project to track all of that work. Another key thing is the boot stream generator. So all of these chips have a container that the boot ROM, in order to load the next stages of software, has to load it and have some metadata that describes it. And so that's what this tool does. For every vendor has their own, they probably have multiple of them. But what we're trying to do is make it accessible, actually make packages that you can apt-get or DNF install. This is, again, not a common thing among silicon vendors. In the future, there's some other ideas that we have that may also leverage existing upstream projects. So, yeah, so at Raspberry Pi, at ADI, there are a number of people that are working really hard on this kind of stuff. It's a bunch of individual people that are passionate about all sorts of things, and that's what pushes the company forward and makes these decisions happen. But it's not always good enough that you just are a single advocate or you have a group of advocates in any given company. Sometimes you also need kind of some financial incentive. And you may think, okay, why do I care about bootloaders? What's the value? But the same thing was said about single board computers. And this is actually really astonishing what Raspberry Pi was able to do. In 2008, a couple founded the Raspberry Pi Foundation to not just make educational boards. So many people think, okay, Raspberry Pi, it's just to be used in classrooms. But even from the beginning, they were thinking about the business side. Originally, the board was $35. Now, their market cap is 719 million pounds. And I think that's the 800 and something million euros, 900 something dollars. That is a massive business. And this value was that they saw that there was not a good software solution on top of these SBCs, on top of these embedded boards. The same thing is true of bootloaders. Bootloaders are the thing that load your operating system. They're the thing that initialize your hardware. And so if you're able to get a really good boot chain, you get more customers, you get more functionality, and you get faster boot time. There's a myriad of different benefits. Those benefits are just like the Raspberry Pi SBCs were in 2008, before Raspberry Pi came along. So you got your advocates in terms of inside companies. You maybe make a pitch that there's some actual value here. You have precedent with Raspberry Pi. What do you do next, right? There is software that we can already use. The boot ROMs, you can't really control so much unless you work at a silicon vendor. But afterwards, in the boot chain, we have our first stage initialization. Mostly this can be thought of as DDR initialization. U-boot is an embedded everywhere. Every vendor of an SoC in embedded uses U-boot. They do their initialization there. Or they have also later stages used in U-boot. There's other pieces of software, other bootloaders, but generally speaking, U-boot has more or less won. It's incredibly popular. So how many people know about U-boot? And how many people know the difference between XPL and U-boot proper? So U-boot itself is actually multiple. It's one source code repository, but it can export, it can be reconfigured to either do the early stage hardware initialization or the final stage loading of the operating system. So in a way, it's two projects in one. Those are very different. The hardware initialization is great. It's amazing that all these hardware vendors are putting their initialization code into an open source project that anyone can build. The second part of that picture is maybe not exactly what we want in the long run. In general, U-boot has done some really incredible things. It has done a bootloader with the kconfig and device tree from the Linux kernel. It has literally copied code and the device trees from the Linux kernel. So you have a bootloader that's quite similar to the Linux kernel, but it's a much smaller community with some extra features. One of those extra features is the U-boot environment. The U-boot environment is like, can be thought of like a scripting environment. So U-boot is C, but you can also write these little scripting, little scripts in this environment. It's kind of astonishing to say it, but these scripts are they're not compiled, type checked, they're not unit tested. The source code is aggregated for many boards at runtime. So your bootloader might even go out to your root file system and get some of this configuration and some of these simple conditionals and stitch it together at runtime. So your build system, your source code repo, doesn't even have the full scripts in their final form. Yes, the source is aggregated from C headers. It's a great debugging tool, but it's not necessarily the best approach for production systems. And even here, even I list analog devices, Mender, foundries, leverage this system, or this tool, because there's a real need. It's a nice scripting environment to be able to put logic in. You don't have to write C code all the time. The problem is, with U-boot itself is not, again, any of these things. It's not unit tested or type checked. We're talking about safety with Rust. There needs to be a better solution for how you write your code for the last stage of this boot chain that loads the operating system. So I've talked a lot about, okay, so there's U-boot, but it kind of sounds like the kernel. Why don't we just use the kernel as a bootloader? So in a boot chain, you have the boot ROM from your vendor, then you do some hardware initialization like you might in U-boot XPL. And then the question becomes, your system is more or less up, you have DDR, you have a lot of resources, you have full system resources. Now you can actually just boot the kernel directly. A small kernel with a very small user space. And that can go out and it can try and find the runtime operating system. It can set up the rest of the system before the runtime Linux kernel runs. So if you think of it like a PC, you get to the boot menu, right? And you might have a couple versions of the kernel. You might have a few different operating systems. You could have different Linux distributions. That type of thing would be done by Linux boot. So rather than, if you've heard of UEFI, writing a specialized C UEFI program that nobody knows how to write, you can write a user space application that does the exact same thing. Rather than using the U-boot environment, you can use a user space application that has all the access to the Linux drivers, the device tree. It has all these standard features that you get. You can write it in any language you want, right? You can write it in Rust, you can write it in Go. So this idea, right, sounds maybe appealing. And in fact, a lot of people have thought of this idea. I think I thought about it myself, not knowing about this for the first time. In fact, in 2005, there was the first implementation. Before then, there were other projects that were doing similar things of copying the kernel. Since then, IBM's Open Power Stack on servers, Netflix has an engineer that's k-execing the BSD, which I won't go into the details of, but is quite astonishing. Google, on many of their servers, are running a version of Linux boot with a Go runtime. So the user space application that is setting up the system, that uses also a Linux kernel. And in fact, it doesn't even boot the kernel. It boots Core, which is a whole other bootloader. When I was working at Bay Libre, one of my colleagues also did a Linux boot. In that case, he was using ARM's TFA to load a Linux kernel that then would load the runtime system. I think in that case, it was even Android. The point is, there's no one Linux boot. There's no project. You can go to Linux boot, the website, where there's a link on this slide. But it is such a powerful idea that it's been implemented over and over and over again. The thing that's missing is bringing it together in a way so that you're not just doing Linux boot, but you have a full boot chain. There are some challenges here, in particular around kexec, when you hardware initialization, particularly when you go between, this is any boot stage, right? In one boot stage, you initialize some hardware, then you go to the next boot stage, and how do you communicate that that hardware is initialized, right? That's a fundamental challenge. Often you'll just kind of initialize as little as possible. In this case, this is all part of kexec. There's some really cool upstream features around that, kexec to make this problem a little bit better and easier. Also, another challenge is around configuration. Basically, the kernel configuration, which has been reused now for a lot of projects, isn't really designed to be used to support a lot of different hardware. There are device trees that are mainline, but there are no kernel configuration files that are mainline. So, yeah. So, despite that, it is a very good approach that has seen many engineers kind of go down this path. So, we have, again, the boot ROM, we have maybe an XPL from U-boot, and then we have a Linux boot to build our full boot chain. So how do we actually implement this? In embedded, really it's much more advanced than it would be in x86. In x86, you would get like last stage bootloader if you're lucky, and then you have no insight into what happens beforehand. In embedded, you have much more control. But despite that, there's basically two large build tools in the embedded space, Buildroot and Yocto. Yocto is a great system, a great build tool. Part of the quality or one of its core features is that it's distributed. So that means that each vendor will have its own layer. So you have a core community-based upstream source code kind of core, but then every hardware vendor has their own separate layer to support their hardware. And so if I want to come to you and say, all of the boards that are sitting on your desks, I can boot them with this binary boot chain, download and run. Doing that in Yocto is going to be more complicated because you're working with this core community, then you have many different hardware vendors doing their own thing, which are not community-based projects. Buildroot has the advantage that it's centralized. It's one source tree with all of this. So if you go to Buildroot today, you'll see a boards directory, you'll see support for exactly this. There is a config file that says U-boot, XPL, U-boot proper, maybe an ARM trusted firmware. Your whole boot chain's already defined there. So if Buildroot already has these, what is there really left to do, right? Like we have our whole boot chain. There are many of them defined in Buildroot already. But there's still a significant part of this puzzle that's missing. Buildroot is really mostly focused on building a user space root file system and the applications that run there. There's still pieces of this puzzle that are missing. So here, part of that is that Buildroot, every board is different, right? Like every board will have a different boot chain. And so it's really any person that supports that board that decides. And there's no standards, it's not consistent. So my proposal is to make that consistent. Through basically leveraging Buildroot, there's a feature that allows you to basically extend it and then eventually mainline that support so that we have consistent boot chains that consist of something like U-boot XPL or core boot, if you've heard of that. and Linux boot to load your operating system. There's other features that are really nice that we can leverage as well. So there's an open project that supports updating firmware. So if you have a Linux distro on your desktop and you have an NVMe drive that has firmware on it, right? And so this service, if you are the right vendor, this service runs, the vendor will upload their firmware to this website and then use this client utility to download it onto your PC. So your NVMe drive's firmware stays up to date. And we can use that same tool, that same system for bootloaders and boot chains. And so basically the general idea is we shouldn't reinvent the wheel. There's tons of existing software here. It doesn't have to be perfect, but generally we need to have some guidelines. That leaves me basically with this. So this idea is something that I hope to advocate for, but much more importantly is inevitably the community. And that always comes back to the beginning of the slides, where we talked about different pieces of software, right? There's Linux, there's RTOS, there's the IDEs and SDKs, there's many types of software that exist. And if we want to get to the point where bootloaders are just as powerful as the Linux kernel, has had as much success, we need to create that community around it. And so that's really my goal, is to try and get some people excited about this topic, that there is a community that exists, we just need more participation. And that's it.